Okay, welcome to your third video in your mini statistics unit. You should have your notes. Turn to page 6. You should also have a bright yellow handout that shows what the Regents cheat sheet it looks like for the normal curve, and also another piece of paper that has 3 normal curves on it so you can practice. Okay, so for this class, we are going to say that when the mean and the median of a set of data are equal, the set of the data is said to be normally distributed. If you take statistics, we might explore that a little deeper, but for our purposes now, that works. The normal curve, which you see down below here, also known as the bell curve, can tell us a lot. So this curve here that's on your note sheet looks a little bit different, but has the same values on it as your cheat sheet that you'll get for the Regent. So I just want you to kind of always have that available so you kind of keep an eye, like what does that look like, what does it have on it. So I'll reference that a few times while I do this little talk. So basically what the normal curve does is if we have data and we know a mean and a standard deviation, by knowing that the data is normal, if we know what the mean is, we can know a lot about where values should fall within this data that we have based on it being normal. So within one standard deviation of the mean, we should find 68.2% of the population. And you can see that on this sheet by just adding these values up. They'll add up to 68.2%. If we go out to 2 standard deviations in either direction, we get ourselves into 95.4% of the data. And then we get out to 3 standard deviations in either direction, we've gathered up almost all of our data, so that's 99.8%. So if you take a test and you're 3 standard deviations above the mean, you should be jumping for joy because that means you're way out here. If you're 3 standard deviations below the mean, you should be unhappy because that means you're way below how other people did on the test. Usually the values that end up out here when what we call the tails are outliers often, and sometimes it's good to be an outlier, sometimes it's not good. One little comment I want to make here, because when you go to MathXL for schools, they're going to talk about something called the 68, 95, 99.7 rule. And they really are referring to these values here, just rounding them in a little different way. And sometimes depending on what book you are using, you'll find these rounded differently. So when you're doing the practice on MathXL for schools, you're going to have to use these values rather than the values that are on our cheat sheet. But I do want to just make one comment, and that is that these values that talk about like what percent of your data is within 1 standard deviation, 2 standard deviations, 3 is not stated on your cheat sheet. So either you need to know those numbers or just realize, oh, if I just add these percents up, that'll tell me what percent's within 1 standard deviation. If I add these guys in, then know what the percent are within 2 standard deviations, and then you can go out to 3 standard deviations. Okay, so let's put this to work in an example down here. So it says the mean of a normally distributed set of data, and those would be our key words, normally distributed, is 56. Standard deviation is 5. In which interval do approximately 95.4% of all the cases lie? So since we have our little handy sheet here, and it's already been clearly spelled out to us that 2 standard deviations in either direction will gather up 95.4%, then that's all we need to do. We take our mean. I'm just going to write the mean right here and put it in the middle. I need to go 1 standard deviation, 2 standard deviations above, and I need to go 1 standard deviation, 2 standard deviations below. So if each standard deviation is 5, when I go above, I'm going to add 5 twice. When I go below, I'm going to subtract 5 twice. So 56 plus 10 will get me to 66, and 56 minus 10 would get me to 46. So I would expect to find 95.4% of the cases in the interval from 46 to 66. Okay, a couple more examples just to kind of help with this. And at any time, if you feel like stopping the video, have at it. Stop it, try the example, and then see if you end up with what I get. Standardized test, normal distribution. The mean is 64.3. Standard deviation is 5.4. What is the best approximation of the percent of scores that fell between 61.6 and 75.1? So I'm going to think about this from a couple different perspectives. So really the question is, if I know that the guy in the middle, the mean is 64.3, I need to figure out under that normal curve what percent are between 61.6 and 75.1. Well, the way our normal curve works is, and you might want to have your templates handy. So here's a template right here. Is it's in terms of standard deviations above and below the mean. Like here's 1 standard deviation, 2. It also, notice, counts by halves on the cheat sheet from the state. So somehow I got to have some relationship in standard deviations to know where this guy sits. So if I take 75.1 and figure out how far above the mean it is, so I'm just going to subtract. That'll tell me how far above, but I want to know it in terms of standard deviations. So if a standard deviation is worth 5.4, then I can take 75.1 minus 64.3, divide that by 5.4, and I come up with an answer of 2. So that is sitting at 2 standard deviations above the mean. Now another way I could do that is I could sit here at 64.3 and I could add 5.4 and then, or add 5.4 to get to 1 standard deviation and see if I'm at the number I want, add another 5.4 and see if I got to the number that I want. So there's different ways to do this. This I think is a pretty handy way because it gets me exactly to where I want to be. Now this 61.6 is below the mean. So if I take 61.6 and subtract 64.3, that tells me how far below. But in order to get it in terms of standard deviations, I'm going to divide that by 5.4. And I'll find out that it's negative 0.5 below the mean. So it's a half a standard deviation below the mean. So in reality then, if I am at this number, 61.6, it's sitting in this position. And my other number, 75.1, is sitting in this position when I'm looking at a mean value, which is the number in the middle of 64.3. So in order to finish the job here, I need to add all the numbers up underneath the normal curve in between those two values. So I end up getting, I can move this out of the way temporarily, 19.1 plus 19.1 plus 15 plus 9.2 plus 4.4, and that all adds up to 66.8%. That's my answer, which is answer number 2 up here. Just one other little thing I want to say, and that is when we do a calculation like this, we are actually finding something called a z-score. So this is a z-score of 2. This one is a z-score of negative 0.5. And really z-score is just kind of a fancy term that means standard deviations from the mean. Okay, so let's do another example. There's all kinds of different applications of this, but if you're starting to sort of understand this whole concept of the normal curve, it gets pretty, they're all kind of the same but different. So weights of boxes of animal crackers coming off an assembly line differ slightly. Form a normal distribution whose mean is 9.8, whose standard deviation is 0.6. Determine the number of boxes of animal crackers in a shipment of 5,000 boxes that are expected to weigh more than 11. So we need to figure out where 11 is hanging out on our normal curve, knowing that we have a mean of 9.8 and a standard deviation of 0.6. So I'm going to come over here. I'll just bring this guy over here, and I'm going to put these numbers. And I think a lot of times these are easiest done by just actually taking the actual curve and putting our numbers on. So if this is 9.8, so I need to get myself to 11. So I know 1 standard deviation if I add 0.6. So 9.8 plus 0.6 gets me to 10.4. I'm not there yet because remember I'm trying to get to 11. And now I got to add another 0.6 and we'll end up at 2 standard deviations above the mean. And sure enough, when I add another 0.6, I'm at 11. So that means that the percent of boxes of animal crackers that are going to be greater than 11 ounces is going to be whatever I get when I add up 1.7, 0.5, and 0.1. And when you add those numbers up, you get 2.3. So I know that 2.3% of the animal cracker boxes are going to actually have more than 11 ounces. You're going to get extra animal crackers. But since they've told us that there's 5,000 boxes, then we can take that 2.3 and change it to a decimal, 0.023, and multiply that by 5,000 and answer the question, because it wants us to know how many boxes. So that turns out to be 115 boxes. Okay, one more example, a little different, but still using the normal curve, the theme of the day. Bring this guy over here in case I decide I want that. Okay, certain school district, the ages of all new teachers hired during the last 5 years are normally distributed. And you'll notice all these problems are going to kind of get in the game by telling you the data is normally distributed. Within this curve, 95.4% of the ages centered about the mean are between 24.6 and 37.4. In this case, we're going to find the mean and the standard deviation. So, 95.4% on the sheet, the page right before this, we've already realized that it means within 2 standard deviations. But if it's June, you haven't thought about this stuff in a while, and you can't remember that, you are going to have to take your normal curve and figure out where is 95.4% of the mean. So you might go through some process where you start adding, and you add these guys up. And you're like, oops, 1 standard deviation isn't enough. And then you go and add these guys in, and you'll find yourself into the fact that within 2 standard deviations of the mean is where you're going to find 95.4%. So now I'm just going to plop this information down here, 24.6 and 37.4. But this time I'm looking for, it's kind of like I'm going the opposite direction. So this time I want to know what is the mean. And so if you notice, the mean is right in the middle of these two values. So all I really need to do is take that average. So I'm going to take 24.6 plus 37.4, divide that by 2, and that'll give me what my mean is. And that is 31. Okay, the second part of the problem is what is 1 standard deviation worth? So if you notice, between these two values that I have 1, 2, 3, 4 standard deviations. So one option would be to figure out what the difference is between these two values and divide by 4, and I'll get my standard deviation. If I want to, I could now use my mean and just go 31 minus 24.6 and divide by 2. So you just have to know kind of what you're working with to figure out what you're going to divide by. I'm going to just use the 2 initial values, so 37.4 minus 24.6, and divide that by 4, and that will tell me what 1 standard deviation is worth, and in this particular case it is 3.2. Okay, so now you should go on over to Math Excel for Schools. There's a stat practice number 3 which will allow you to practice with this a little bit more. Just remember that there's reference to this thing called the 68, 95, 99, 7 rules, which is a little bit different than the values that you'll see on our cheat sheet.